Yeah. So thank you for the introduction. So today we are going to see about the application of hydrology and hydraulic modeling for flood management. This is Guganesh Sankar, Assistant Engineering Manager in L&T Construction. So the floods are the recently occurring natural disaster, and everyone are aware of it. So this is it is a type of disaster where the overflow water submerges the land nearby, which is usually dry. So it is often caused by heavy rainfall. The major contributor is heavy rainfall, continued by rapid snow melt or storm surge from tropical cyclone, etc. And it causes a major loss of life, damage to personal property, and critical infrastructures, etc. So there are main types of flood. One is river flood. It occurs nearby the flood where the river water overflows the nearby land. And another type is flash floods, where the extreme rainfall occurs within a short duration of time. And the other type is man-made floods, where the structure failure like dam failure, etc., causes the flood. And another type is coastal flood, where due to tsunami or a storm surge, the coastal water inundates the nearby coastal areas. And urban flood is due to the improper or inefficient storm drainage network, where the water overflows the near the city, etc. And another is fluvial flood, where both rainwater as well as the nearby lakes and ponds, etc., causes the floods. So to predict these floods, we need to model the nature of the landscape. So flood modeling helps us to predict the flood, and it accurately measures the quantity of water and how depth the flood may occur, and for how much duration the flood may occur, etc. So it is crucial. It allows us for accurate prediction of flood events, which helps us in for enabling the effective flood risk assessment, informed decision making, etc. So this this flood modeling helps us to identify the detailed information about the inundation area, flood depth, and timing, etc. So these are the major softwares that can be used for flood modeling. There are three parts like the GIS tools, hydrologic modeling, and hydraulic models. In GIS tools, the ArcGIS, GIS can be, QGIS can be used. For hydrologic models, the HMS, SWAT, and other proprietary softwares are there that can be used. And for hydraulic modeling, HECRAS, SWMM, and other AutoCAD models are there that can also be used. So this is the process of flood risk assessment. Starting with data analysis, we will be collecting the all required data, rainfall data, LULC data, soil data, and digital elevation model data, etc. So then we'll be proceeding with the GIS processing, where we'll process the collected data, spatial data, and we'll process and we'll calculate water delineation using GIS. And then next, calculating the watershed, we'll move on to hydrologic analysis. Here we'll completely model the terrain based on the digital elevation model, watershed delineation, and including the rainfall analysis. So here, this process is very crucial, where we'll be converting the design rainfall into design runoff. How much runoff will be simulated, etc. So after identifying the hydrologic analysis, we'll then move to flood modeling. Here, hydraulic analysis will be done, where will will give the peak discharge estimated using hydrologic analysis as input, and will simulate the movement of water across the river or channel, etc. And will identify how much depth it inundates, it's whether it overflows or etc. Like that we can identify. Then comes the prevention and reduction process, where we can provide any mitigation measures, where we can provide any like structures to block the overflow of water, or we can divert the flood water to another nearby channel, etc. That can be modeled, and we can manage the flood water. This is the entire process for flood management. So coming to the first part, rainfall analysis. So this is the major input for hydrologic modeling. It can be obtained from meteorological stations, rain gauge stations, which are maintained by IMD, and as well as there are many rainfall stations across the country, which are maintained by agriculture universities and other AWS network, etc. So that rainfall stations can be used. If some areas where there is no rainfall stations, then you can go for isopluvial maps. This is derived based on the long-term rainfall with nearby stations, and they have made a spatial map across all over India. So this is available with IMD, and if then other data are remote sensing data that can be also used to estimate the precipitation. So the techniques like a Thiessen polygon will be helpful for estimating the rainfall for a particular catchment where where the rainfall is spatially distributed. So after identifying the collecting the rainfall, we'll be then deriving the intensity, duration, frequency curves, IDF curves, which are commonly used for design of hydrologic and hydrologic structures. So this is the relationship between the uh, total rainfall intensity, duration of rainfall, and as well as the frequency of rainfall. Frequency denotes the return periods, where the return periods are generally the expression of probability of exceedance value. So these IDF curves are obtained through frequency analysis of rainfall observations. So next, coming to watershed delineation. So we'll be collecting the terrain characteristics from the digital elevation model, and the digital elevation model consists of elevation values for a particular point. Each that will be divided into grid points, and each grid point will be having a elevation point. So based on this spatial information, we will be delineating the watershed. So watershed is what particularly the contributing area of a particular pore point, where example, if this green color area represents the watershed, if any rainfall occurs over this area, it all collects and accumulates at one out pore point, which is highlighted in red color. So this is the watershed area. Like this, likewise, there are sub basins and small particular area based on the pore point which requirement. So this watershed delineation can be done using GIS process, which is crucial for watershed flood risk assessment. It is based on data integration, spatial analysis, and visualization to support the flood mitigation planning, etc. So the GIS tool analyzes the digital elevation model to determine water flow path, define the stream networks, and delineate the watershed boundaries for flood risk assessment. So next, we are going to see about the hydrologic modeling. So here we have started using HMS software for hydrologic modeling, which is developed by US Army Corps of Engineers. This HMS model comprises of three components: basin model, meteorological model, and control specifications model. So the basin model represents the physical watershed characteristics of the basin, and it includes sub-basin, reaches, junctions. So this basin model includes all the spatial informations like curve number data, land use data, soil data, etc. And the meteorological model contains precipitation inputs. So we have I analyzed the rainfall for the particular area. This rainfall is converted to IDF curves, and from IDF curve we will be calculating the hydrograph that is given as the input for the hydrologic modeling. Then coming to control specification, we will be defining the time span, time interval, and duration of the simulation for hydrologic modeling. So this is the representation of hydrologic cycle, where the water is transported from ocean to atmosphere through evaporation, and then the condensation process. And major part of the water cycle is precipitation, where it falls back into the terrain, and from there it converts into a runoff, and then it flows through river, and again the process cycle continues. So to simulate this water components plays is the major part of the hydrologic modeling. So here I have shown some process like how to set up the hydrological modeling. So initially it is a representation of a pump house which we are studied. So initially we have placed the pump house layout, and we will be delineating the stream, whichever streams, like based on the digital elevation model. Uh, what are the lower areas will be delineated as a stream network, and based on the stream network we will be delineating the watershed. So this watershed, based on this watershed, we will be setting up the hydrological modeling. So for each subbasins, individual characteristics will be analyzed through spatial information like land use, soil, and curve number, etc. will be analyzed using spatial information in GIS, and then this base hydrological model will be set up. So once this hydrological model is set up, then we will be giving the rainfall data as input. So you could see that dark blue color as a rain precipitation input, and the red color represents the loss in precipitation. The loss may be due to infiltration and other etc. So that loss is removed, and then remaining excess of this rainfall is converted into runoff. So this runoff hydrograph is generated using hydrologic model. Once this is generated, then we are going to analyze the hydraulic modeling. So this is done using across software. So same, it is also developed using United States Army Corps of Engineers, and it comprises of following components. Like it includes steady flow water profile computations. It can be done a 1D or 2D and unsteady flow simulations, and water quality analysis also can be done using this across components. So after identifying the hydrograph, then we have to calculate the cross section of the river profile. So that can be calculated using the DEM data, which will be procured using any, as you mentioned, by using, it can be procured using drone technology, lidar survey, etc. So using that high resolution DEM, we will be extracting a cross section for a particular interval. So it is based on the study area, like how much duration, how much extent you need to study. Based on that, you can draw cross section lines. So the green color cross section lines represent the cross section, and the blue color center line represents the river center line, and the light blue color represents the flow extent. So how much area you are considering for the study. So once this model is set up, then we'll be giving the peak hydrograph as input. So we are calculated using the HMS software. So that peak hydrograph will be given as input to the across model, and will specify the time span, time interval, etc. And the output will be simulated as shown in this figure. So this is the water depth. How much water depth will be flowing to the river, and how much water will be overflowing to the nearby land area. So that is also model using this. So this is a typical cross section of the particular cross section where the water level is water depth is calculated. So these outputs are very crucial for any infrastructure which is located nearby the rivers. Like example, in our case, there are many pumping station. Lift irrigation system includes many pumping station which is located nearby the river. So the work of the pumping station is lift the water from the nearby river and to uplift for the irrigation purpose. So to protect the pumping station which is nearby the river from any flood, this flood management is very crucial, and this flood depth and extent is simulated for the pumping station, and subsequently if it is safe, the pumping station can be kept at the elevation, or based on spatial information it can be moved to the nearby locations, nearby area where there is no flood inundation. etc. That can be done. And based on the flood depth, we can mention the high flood level for the pumping station, and based on that, they will keep the FGL above the HFL so that it will not be affected by the upcoming any flood, etc. So here I will provide you a case study about how we are studied the Adyar River and Velachery area. So we have procured satellite images from Landsat, and we have demarcated the land use from the Landsat images. For 2006 as well as 2016, we have identified the land use data. So these are the land use changes from 2006 to 2016. Here you can see that there is a drastic change in the settlement and barren land, and there is a reduction in water bodies, etc. So for this Chennai area, we have taken rainfall data from the Meenambakam station, and we have collected more than 30 years of daily rainfall data from Meenambakam station, and we have calculated the IDF curves for that particular station. So it is based for the 2 years to 100 years return period. And this is a drainage network for Velachery area. So Velachery area we have studied, and this is based on 2015 Chennai floods. So we have taken two major spots. One is Velachery and Adaya River. So for Velachery area, we have collected the drainage network map from the Chennai Corporation. So this is three wards representing the Velachery area: 178, 177, 179, and the red color points represent the DGPS survey that was carried out, and we have taken DGPS instrument to each location of the stormwater network, and then extracted the elevation of particular elevation of the manhole and the stormwater corners wherever there is a change in direction. We have taken elevation data, and we have based on this elevation data, we have modeled that elevation profile into SWM model. SWM is another software where it can be used for a stormwater delineation network. And here we will be providing the invert elevations of the nodes, stormwater vertices, corners, and manhole, etc. We will be providing the size and depth of the drains, and we will be providing the impervious area of the area, slope rate, etc. And again, we will be providing the IDF curves, and we will be delineating the subbasins based on each drainage network, each stormwater network. So based on that, we have delineated the subcatchments, and then from the subcatchment delineation, we will be creating the stormwater network. So this is the simulation report. So for each return period, like 2 years to 100 years, we have estimated the precipitation and infiltration loss, and how much is the surface runoff, etc. So based on the return periods, we'll simulate like how much nodes, each node represents the vertices of the stormwater drain. So how much nodes is getting flooded, with that we have identified in the SW model. So for 2 years return period, the number of nodes represent 51, and it keep on increasing for 100 years return period. So for 100 years return periods, there are 81 nodes it gets flooded. So these nodes are classified for within time interval. So 0 to 5 hours, there are 21 nodes flooded for 2 years return period itself. So likewise, we have classified based on the time interval, and this is the spatial representation of the uh, runoff and node flooding for 2 years rainfall return period. So you could see that red color represents flooding area. So this is for 2 years return period, and simultaneously we will be doing for 5 years return period, 10 years, 50 years, and 100 years. So you could see a difference in the map where the red color nodes are increased drastically for 100 years. So for 2 years, there are only 10 to 12 points it gets flooded, but it keep on increasing, and for 100 years there are many areas it is get flooded. So from this, and we have identified the vulnerable hotspots. So which are the points where it is very vulnerable to 2 years to 100 years return period flood. So this is the area. And so some of you, if you are living in Velacheri, you could identify the locations. So the main Velacheri 100 feet road itself is very highly vulnerable. And so we have provided some mitigation options also for Velacheri area. So the water from the Velacheri area flows to the Pallikarnai marshland, and from Pallikarnai marshland it flows through OKM Madu and then joins to Buckingham Canal. So we have identified the exit of the Pallikarnai marshland through OKM Madu, where the exit the drainage is very insufficient to carry this much of flood water. So we suggested to increase the flood depth, flood extent drainage length into from to 120. It was 120. So from 120 we suggested to increase 200 meters for OKM Madu. So this is the discharge, and based on the suggestions, like when one channel the width was 120 meter, this much is the flood depth, and when channel width is 200 meters, the flood depth is drastically reduced. So this was one suggestions we have given to the, actually this report was submitted to State Planning Commission. So we have submitted this suggestions. So the minimum width recently we have seen the changes in OKM model. They have increased the channel width, so that is a good thing. And next we will be doing the fluvial flood modeling, where we will be concentrating on the Adayar River. So this is the peak discharge for different return periods for the Adayar River. So each tributary is modeled in HMS, and the final Adayar river carries 3000 meter cube per second for 100-year return period. So the 2015 floods was more than 100-year return period floods. So they have simulated around 5000 to 6000 meter cube per second for Adayar river. So based on the HMS modeling, we have mapped the flood inundation for 2-year return period. Simultaneously, we have done for 5 years, 10 years, 50 years, and 100 years. So you could see where the Adayar River, where near the airport and other joining area, where the inundation area gets rapidly increased for 100-year return period flood. So this much area was inundated in the 2015 year flood. So this is the cross-sectional profiles, some cross-sectional profiles we have done for across modeling for near the Koturpuram bridge, where the nearby areas flooded during the 2015 flood, and near Trivika bridge also we have modeled the cross-section. So this is the summary of the results, where for 2 years return period, the flooded area was 32.5 kilometers square, and it keep on increasing, and for 100 years it is 51.8. So there is a change, 59% increase from the 2 years return period. So for mitigation options, here we have identified like a Muduchur area, which is very much affected during the 2015 flood. So we went to site visit and took the aerial survey for around the Muduchur area, and we identified that before construction of outer ring road, there was not much flood over the Muduchur area. And after the construction of outer ring road, there was drastic flood these things impact. So we, to prove this one, we modeled 2D modeling for over the Muduchur area, and we have provided the DEM data. Then we corrected the DEM based on the older period. So this DEM is without the outer ring road, and then we modified the DEM with the measurements of the outer ring road, and based on that, you could see that the dark blue color indicates water gets stagnated to the left hand side of the outer ring road. This is because the outer ring road does not contains any that much sufficient conduits between to flow the water from one left hand side to the right hand side. So there were insufficient, and then that was noted, and we have suggested to State Planning Commission, like existing drains to be properly maintained, and we adequate drains to be provided across outer ring road and its surroundings to increase the free flow of water flood. So constructing a drain along the service road of Madurai bypass to divert flood water into Adaya River was also suggested, and proper channelization of Adaya River of the upstream is also required. Since there are many sediment and the channel width is reduced in the upstream side of the river, that needs to be channelized. That can reduce the flood depth around the area. So this was the study carried out with the help of Center for Water Resource Analysis and Center for Climate Change and Disaster Management. So, and this is one flood simulation done for a particular irrigation projects where there needs to be a bund constructed across the village. So this is due to because they are going to increase the capacity of the reservoir, and so they need to construct a bund over this village to protect this village from the increase in the reservoir depth. So we identified and suggested that the rainfall runoff for this particular village will flow in this area, and this village may get inundated using that. So it was not accepted by the design members. So we did a flood simulation analysis. So we have provided the design rainfall in, and we have carried out the flood simulation for the particular village area where the water will be flowing from the higher terrain to the lower one, which crosses across the village. So this was visualized using this flood simulation, and we submitted this to the design team, and then they were satisfied, and then they changed the bund construction plan to a different strategy to increase the reservoir. So these are the case studies where we can use the flood modeling to a useful and a very critical resource, which it can be protected to protect the infrastructures, nearby villages, people living nearby coastal areas, etc. So that's all from my side. This is the conclusion. So hydrology and hydraulic modeling are crucial tools. Both integrating both models improves flood prediction, and data accuracy and calibrations are essential. So for calibration, we there are many data available with the Central Water Commission, and you can use that for model calibration as well. And if it is not there, then you could take any flood discharge measurement devices and take the measurement and do the calibration. So that will be that will provide very reliable results. And there can be future advancements such as AI and remote sensing for for enhancing the flood management modeling. And effective flood management reduces economic loss, life of people, etc. And the ongoing research and technology innovations are necessary for sustainable solutions. So that there needs to be a connection between the research and then the implementation. So thank you all. These are recent publications we have published. This is published during working in L&T construction.